Okay, so now we're going to go back to the scenario with the cyclist, our observer, and the fire truck, our source. Only now the cyclist is stopped at a traffic light. So the observer is now stationary and the source is moving towards that observer. Now, as you've seen in this scenario, when the fire truck emits a sound wave, it travels a distance so that it's getting closer to the sound waves once it has emitted them. And as a result, the wavelength actually decreases. So between each crest, it travels a distance Vs, the S subscript here stands for source, so that's how fast the fire truck is, times T, where T is the period. So this is how much closer it travels to the previous crest before emitting the next crest. We could also write this as Vs on F, where F is the frequency, and that's just because the frequency is the inverse of the period. Okay, so we can use this to work out what frequency that observer observes. So the observer now sees a shorter wavelength. The wavelength that they actually see is the initial wavelength emitted by the source minus that change in wavelength, which comes about because of the source moving towards the observer. So the Vs times T, which we said was the same as the Vs times F. So this is the new wavelength here observed by that observer on the bike. So the frequency observed by the observer on the bike is the velocity divided by the new wavelength. The velocity of the sound through the medium doesn't change. And so this is equal to V over lambda minus Vs on F, that's just this one. And so we can substitute in for lambda here, that's the initial wavelength, the wavelength from the source. That's equal to the velocity over the frequency from the source. And so we can pull the 1 on F out on the denominator as a common factor, which brings it up the top into the numerator. And so we've got F dash, which is the frequency observed by the observer, is equal to V over V minus Vs. This is the velocity of the source, and the V stands for the velocity through the medium, times the frequency, which is the frequency emitted by the source. So this is what happens when the source is moving towards the observer. Now, once the source passes the observer and is moving away, in that case, as you saw in the little animation, the wavelengths get more spread out, and you can actually show that they increase by the amount Vs on F. And so in that case, the observed frequency is given by V over V plus Vs times the frequency of the source. So what we can do now is combine these two situations. If both the observer and the source are moving, then the new frequency, F dash, that observed by the observer, is given by V plus V naught, where V naught is the velocity of the observer, over V minus Vs, where Vs is the velocity of the source, times the frequency produced by the source. Now, note that these signs are for when these two things are moving towards each other. If the observer was moving away from the source, then this would be a negative sign. If the source was moving away from the observer, then this would be a positive sign.
Okay, so what I've got here is known as a Doppler ball. This Doppler ball makes a really annoying sound when I turn it on, like this. Now what I'm going to do in a minute is swing this ball around my head. Before I do that, I'm going to take this microphone off and place it in the middle of the lecture theatre to pick up the sound. I want you now to make a prediction about what you think is going to happen as this Doppler ball goes round and round and round. There's a big hint in the name there.